Hi, I'm excited to tell you about some of our work on responsible data-centric AI and applications in healthcare and medicine. So my group here at Stanford develops machine learning algorithms for biomedical and for healthcare applications. Right? We're very interested in both developing these algorithms and also in deploying them into practice. So here's a couple of examples of things we've done recently. We've developed these computer vision systems for looking at these cardiac ultrasound videos and to assess basically heart functions and cardiac diseases from these ultrasound videos. We've also algorithms for using machine learning to improve the clinical trial design process. Right? So these are now being used by some of the largest biopharma companies. So one interesting challenge is that, as we're thinking about deploying healthcare AI systems in medical context, it becomes really important to think about how to carefully audit and to evaluate these machine learning models. Just want to give you a concrete example, which is actually comes from a sort of a detective story that we had to recently solve here at Stanford. So the context of this is that there's been a ton of interest in developing AI systems, especially for dermatology applications. Right, so you have algorithms, which is like the following, like the ones shown here, that can take as inputs photos, right, of someone's skin lesion, and then try to predict from that photo, like how likely this image is to have a skin cancer. Right, in this case, it's likely to be melanoma, and the recommendation is to visit a dermatologist as soon as possible. The reason why this is very compelling from a healthcare perspective is that these kinds of photos of skin lesions are relatively easy to collect, right? So anyone with a smartphone can take photos of their skin lesions. And also, there are many underdiagnosed skin cancer cases, right? Every year around the world, there are millions of these underdiagnosed skin cancer cases. Right? So if you can catch them early, then that can potentially save a lot of lives. So here at Stanford, we're very interested in trying out potentially some of these technologies for diagnosing skin cancer. Right, so we took 3 of the state-of-the-art models, including some from commercial vendors, and we evaluated here at Stanford patients. Now, these models, they all have actually very good performance if you look at their original reported papers and publications, but the AUC is often above 0.9. So when we apply these models to actual patients' data from Stanford, the AUC was actually 9 to about 0.6. And just to be clear, these are actually real Stanford patients. There's no perturbations to data, which actually took their images directly from the electronic healthcare systems. So the puzzle, right, the mystery that we want to solve is, okay, so why did this happen, right? Why did these models' performance drop so much when they're applied to the actual patients? So, and did a systematic audit to try to identify what are some of the issues, right, with these models that led to this drop-off, right, from the original reported AUC about 0.9 to about 0.6. And I think this is going to be illustrative and will set the broader context of why we want to have this data-centric perspective on responsible AI. So it actually turned out that the first, one of the biggest reason why that contributed to this drop-off is actually there were a lot of label mistakes. So it turned out that the original test data, the original images that was used to test and to evaluate these algorithms had a substantial number of mis-annotations in labels. So what happened was that the original test data sets for these algorithms were mostly generated by having dermatologists visually looking at these images. Right? And the reason is be easy to collect that kind of data, right? So the dermatologist will look at the image and say, is this skin cancer or not skin cancer? And it turned out that dermatologists visually inspecting these images also make a lot of mistakes, right? So the actual ground truth, which is what we use here at Stanford, comes from taking a biopsy of the skin lesion and then doing pathology testing to see whether it's skin cancer or not. Basically, compared to that ground truth, which we have, the visual inspections that's used to annotate test data sets actually had a lot of mistakes. And this actually can contribute to about half of the drop-off in the model's performance. A second big factor, right, is that there's actually quite a substantial amount of data shift. right? So the original models were all evaluated on relatively common skin cancer diseases. And here at Stanford, our data set had both common diseases and also less common diseases, right? So that data shift, right, in this disease models drop off. So the third factor, which is also critical, quite crucial, is that we discovered that all of these algorithms, they had much worse performance when they're applied to images from darker skin patients, right? So specifically, if you look at the sensitivity of the model, which is if the patient actually has skin cancer, how often would the algorithm say that they have skin cancer, right? So that's what we really care about. The sensitivity is actually quite poor in images from dark skin patients. And when we look deeper into this, we discover that actually there are very few dark skin images in the original training or test data sets for these models. So this is one case study that we did, right, looking into dermatology AI models, where we discovered there are a lot of challenges in the data that was used to train to evaluate these models. Now we did, in related works, we also did similar kinds of audits for many other medical AI systems that were approved by the FDA. Right? So the FDA is sort of the gold standard for approving medical-related interventions in drugs, vaccines, and including AI systems. So we looked at over 130 FDA-approved AI systems. So they're just summarized in this plot that we have here. The paper that we had described this in more detail. Right, so each of these symbols corresponds to one of these FDA-approved AI algorithms, and I stratified them by which body part they apply to. So there are a lot of interesting information that we discovered here, but maybe the main thing that we want to notice here is that actually 93 out of these 130 AI systems that we audited reported only performance from one location, right? Moreover, 126 out of 130, the evaluation is done on retrospectively collected. Right, so that means that it's possible for these algorithms to be evaluated on previously collected, maybe benchmark data sets, and from one location. And as we saw from this, the case study of the dermatology AI models, right? So these kinds of limited evaluation at one location on retrospective data can potentially mask a lot of limitations and weaknesses and biases in the models. And we've also shown that the performance of the model can be highly variable, depends on which locations are tested on. Right, to illustrate this, right, I'm showing you sort of 3 models that are used to detect pneumothorax from these chest X-ray images. Right. So they were trained at these 3 different locations, right, Stanford, Boston, and NIH, and they were also we also applied them, evaluated them on data sets, on test data sets from these 3 different locations. Diagonal here corresponds to the performance of the model when it's tested at the same location where they're trained. And the off diagonal corresponds to when it's tested on data from different locations. And you can see it's actually quite apparent that the model's performance on new test locations can sometimes be substantially worse. Right? So for example, for the bottom row here, there can be a more than 10% drop off in the model's performance when it's tested at different sites. So all of this, I think, highlights the importance, right, of really taking a data-centric perspective in biomedical AI, both in building the AI systems and also quite critically in evaluating and monitoring the performance of these AI systems. So for the rest of the presentation, I want to just quickly highlight sort of 3 sets of areas we've been working on improving, and lessons that we learned in improving response data-centric AI for biomedical and healthcare applications. So first is related to data maps, which is the idea of really characterizing what is the landscape of the data that's being used for different biomedical algorithms. The second is on, once we identify critical limitations in existing landscapes of data sets, try to create new data sets. And the last point is about doing more data evaluations as a way to clean and to improve biomedical data. So data maps. So the idea of a data map is basically to create a comprehensive mapping of the landscape right, of a particular domain to see what kinds of data are available and what kinds of data are being used to train and to evaluate all of the algorithms in that domain. Here's an example of a data map that we created for dermatology as our running example. Right, so each of the squares here corresponds to one of the AI dermatology papers. And while each of the circle corresponds to a data set that was used to train or to evaluate the particular algorithm in that paper. Right, so they're linked together. So what's interesting is that the color of the circle corresponds to whether the data set is private, if it's colored red, or if it's a public data set, it's colored green. Right. So the private data sets are basically the ones that nobody really can have access to. And the size of the circle is proportional to how big that data set. So one thing that's kind of interesting is that you can see that there's a couple of large public benchmark data sets, like data set 1 here, that's used to in many of these papers. On the other hand, right, for about half of the papers, especially the ones that are on top here, most of them were trained and evaluated on relatively small private data sets, right? And based on our experience with auditing the systems here at Stanford, we can see that there are warning flags and limitations potentially in these algorithms that were trained and evaluated on these private data sets. We also learned from doing this data mapping, right, that actually most of the existing data sets have very few images from dark-skinned patients, and many of them are very noisy in that they did not rely on the ground truth annotations from taking biopsy samples. So to address that limitation, we diverse dermatology images data sets, which is the first data set, the public available data set that has these high quality labels, right, from biopsy annotations, and also covers, balanced images, right, from across all the different diverse skin tones. Right, so this is what's work led by my postdoc Roxana in this upcoming paper, and this data set is available for our researchers and for the community to use to benchmark their model. And we've shown, right, in this paper that actually fine-tuning these existing dermatology AI models on our new diverse dermatology images data set can substantially improve the model's performance, especially among its performance on dark skin images, right? So the green bars here basically corresponds to the performance of the model when it's fine-tuned on this data set. So another limitation, right, in a different domain that we identified is that there are actually very few medical video data sets, right? And to address this, we also released EchoNet, which is I think one of the largest, maybe the largest publicly available data set of medical videos, right? So it has these ultrasound videos of the heart, and we also have annotations about different medical annotations from the heart. And we've used this data set to develop this model that I mentioned in the very beginning, right, where we use computer vision to assess cardiac functions directly from these cardiac ultrasound videos. This work was led by my postdoc, David, and student Brian, and it was published in Nature, and we're currently doing more in-depth evaluations and deployment of the system. So this data map, right, helps us to in existing data sets, and then we can create new critical data sets to address those limitations. In addition to creating new data sets, right, we also find it's very important and helpful to think about different ways to increase data accountability, right, in the machine learning pipeline. And here I just want to briefly share with you some of the work we've done on using this idea called data Shapley values to increase and as a way to improve the accountability of these data-centric machine learning pipelines. So the idea of data Shapley, right, is the following, right? So in most of these machine learning pipelines, right, so we have these 3 different components. We have some training data, which can come from different hospitals or different vendors, different sources. We have our favorite learning algorithm, which could be gradient XGBoost, or could be your favorite neural networks, and you have interested in, right? Which in our case, oftentimes is the deployment performance, right? The accuracy or the F1 score the models in deployment. So data accountability basically means that if the model achieves some certain levels of performance that I care about, right, in deployment, for example, I would like to attribute that performance, maybe this 80% accuracy, back to the individual training data sources, right? 0.8 back to the original sources of the training data. And similarly, if my model makes mistakes or exhibits certain biases, I would also like to identify which training data might have contributed and led to that bias because of maybe mis-annotations or noise or other spurious correlations in the training set. Right. So if I can achieve this whole entire pipeline, right, of accountability, then I can potentially improve the quality and the transparency of my entire machine learning system. So data Shapley value is basically a method for assigning these evaluations. Right. So I won't go into too much detail here, but just want to highlight that we have a series of works, including some quite recent works for computing these data Shapley values, and also in a scalable ways that can be scaled up to very large data sets of hundreds of thousands of images, for example, algorithms. So I want to quickly demonstrate what is the output of data Shapley value and how we can use that in practice. Right. So going back to our running example of dermatology AI models, right? So we have our training data sets, and we see that the training data set can often be very noisy, right? It can have mis-annotations. And the model that's trained on this data set, when it's deployed in the clinical settings, right, the performance, as we saw, can be quite poor. There's a drop off in the model's performance. So data Shapley value basically assigns the score to each of the individual training image. The score could be positive or negative, right? So score is negative. This indicates that that particular image is detrimental to the model's performance in deployment, right? Maybe it's introducing some label noise, right? Or maybe it's introducing certain spurious correlations in the model. The score, if it's a positive, that means that that particular image is quite informative, right? And to make good decisions in practice. So it's actually very useful to have these scores, right? And one thing we can do with them is that I can weight my training data, right, based on these Shapley scores, and then simply retrain my original model on this weighted data set. Right? So this basically encourages the model to pay more attention to data sets, to data points, right, that's more informative, and attention to data points that are likely to be more noisy. And by doing this weighted training, right, this can substantially improve the model's performance in deployment, right? And in this case, by over 10%. And the benefit of doing this is that it's actually very easy to do, right? We didn't have to go out and collect additional new data, right? So all that we needed is the existing data that we have already collected. So the data can also help us to identify these mis-annotations, which is quite prevalent, as we saw especially in medical data sets. Right. So we applied this approach to this CheckSpurt data set, which is a very large data set that's commonly used that contains these chest X-ray images. And what's really interesting and striking is that we found that when we looked at these images that had low or negative Shapley scores, we asked a panel of experienced radiologists to annotate those images. And we found that 60% of the images that had these low Shapley scores were mis-annotated in the original EHR, in the original database. And we showed that by removing these poor quality and mis-annotated images, right, that had low Shapley scores, we can substantially improve the model's performance because then the models be trained on the remaining data sets, which are quality and much cleaner. Right, so the data Shapley scores can also be this effective approach for cleaning data sets by removing noisy samples. And oftentimes, right, the performance gains from removing these noisy samples with these data Shapley scores is actually much larger than the performance gains by trying to change different model architectures on the original noisy data set. Right, so here's an illustration of this, right? So the green curve corresponds to taking one of these models and we denoise the data set using the Shapley scores, you can see that we can really improve the model's performance quite substantially. And the different red curves corresponds to different ways of training the model using different architectures, right? But it's trained on the same noisy data. And when it's trained on the noisy data, the model's performance often saturates, right? So there's much greater improvements potentially coming from this data-centric cleaning of the data set. So just to summarize, right? So I think so I hope to illustrate that, especially in biomedical AI settings, healthcare applications, right? These data-centric questions are especially important, and it's really important to take this data-centric perspective in both in training the models and also in evaluating the models. And we've also shared sort of 3 main lessons based on our experience that we found to be very helpful practices and helpful methods of our data-centric pipelines, right? The data maps helped us to really have a holistic way to see what kinds of data are being used in a particular application domain. And by looking at those data maps, we can identify what are the critical gaps in the data sets, which help us to create and to identify new data sets that we can create to contribute to filling in those gaps. And data evaluation, I think, is quite a nice and general approach for further improve and to clean the data sets. And here are some of the key references for each of these methods I described. So I just want to stop here and thank you for your attention. So all of the papers and data and codes are available on my website. Just want to really acknowledge again the terrific students and postdocs, Roxana, Eric, David, Amirata, Yunchen, and Wei Xing, who really led this works. And also want to thank my collaborators. Thank you.
Awesome. That was such an amazing talk. Thanks so much, James. I particularly like the analysis investigating why Derm AI didn't work on the Stanford data set. And you also provided some great solutions to solving some of these challenges that you mentioned. And I think
thank you very much.
And I think the importance of this data-centric AI approach really becomes eye-opening, especially in the context of healthcare applications. Awesome. With that, we have a bunch of questions in the Q&A tab. The first one is from Alec, and they say, how are we able to effectively gather data to properly detect and classify new diseases and viruses? With COVID-19 and now monkeypox, it should be a priority for pandemic prevention.
Yeah, that's a great question. So I think actually a lot of the really useful, exciting data are already collected. They're sitting in different medical records. And I think there's a lot of value to be gained in just leveraging the existing data sets in the medical records to be able to do detections of new viruses or studies of COVID-19. And we've done some works on those fronts. I think this is also where the data-centric perspective becomes really critical, because a lot of the data is sitting in these medical records, but they're often very hard to work with for computer scientists and for machine learning folks, right? So because it has a lot of unstructured data, it requires a lot of data cleaning and data selection, data curation. So this is actually, that's why I think actually this kind of healthcare biomedical data is a perfect and one of the most impactful areas of more data-centric advances.
That makes a lot of sense. We do have another related question to COVID-19. Alex says COVID-19 has had a lot of impact on historical medical data, and they're considering excluding that data from training since it's so unusual. Are there any other approaches that people are using?
Yeah, so that's also really interesting. We've had similar discussions of how to deal with COVID-19 data in some of our works, looking at like clinical trials. Right? For example, you have clinical trials that happened before COVID-19, like maybe in 2019, and then you have the ones that more in the last few years. And we found that in some of the cases, it's actually better to not just throw away all of the data from before the 2 years ago, because that really does remove a lot of useful information, a lot of data. I think there are also interesting approaches to still keep the data, but keep data from prior to COVID-19, but use other ways to like adjust these distributions to make them more comparable.
That makes a lot of sense. If you're just deleting some data from your entire training set, then you're kind of losing other information that could have been very useful for training. Makes sense.
Exactly.
Next question is from Fu, and they say, this is a little off topic, and they've read that there are some security concerns regarding medical data used in machine learning. And
Yeah.
they're wondering if this is still currently a problem in AI healthcare. If yes, do you happen to know some of the steps taken to protect the privacy of patients? And if no, do you know why this is no longer a concern?
It's also a very good, interesting question. So I would say it's still an ongoing concern about security and privacy of the data, especially from the perspective of the hospitals, right? Because if they own the data, then they could potentially be sued if the data becomes leaked or become public. For many of the patients, on the other hand, I think many of them are actually excited to share their data and make their data available, especially for medical research. Right? So there are efforts in the US, like these All of Us projects, and in other countries where patients, up to like millions of patients actually share their genetics data for research purposes. Right. So I think there's like this interesting trade-off. And one area going forward is thinking about how do we go directly to the patients. So basically bypass the hospital, go directly to the patients and get the most useful data directly from the patients. On the machine learning side, on the technical side, there are also interesting approaches to try to mitigate these potential security concerns. So it's one of the areas that we're actively working on, is looking at synthetic data and how to generate synthetic data that have good privacy guarantees. So it doesn't leak sensitive information, but are still high utility.
That makes a lot of sense. Thank you so much for sharing. We have a bunch of questions in the chat, but unfortunately, we're kind of running out of time, so we will not be able to get to all of them. But in case the attendees want to reach out to you to ask their questions directly, what would be the best way to connect with you?
Yeah, so please feel free to email me directly. I'm happy to follow up, happy to respond.
Thank you so much, James. It was a pleasure having you here. We learned so much about data in healthcare. Thank you so much.
Great. Thanks for hosting this.
Of course.